If you want to catch an AI being jailbroken into helping with a bioweapon, the standard trick is to bolt a second model on top as a safety filter. It works, but it is expensive. This paper from Anthropic asks a simple question. What if the monitor reused the computation the main model is already doing, almost for free? Here is the cost problem in one number. Anthropic's earlier constitutional classifiers work showed that a separate safety model adds real robustness. Using Claude 3.5 Haiku as a filter for Claude 3.5 Sonnet pushes inference costs up by about 25%. For a frontier system, that is enormous. The core idea is representation reuse. Prompt classifier reads the exact same input text as the policy model, so it can share the policy model's computation instead of redoing it from scratch. Rebuild the safety monitor out of representations the model already produces, and the overhead almost disappears. They explore 3 families of cheap monitor. First, linear probes on the model's activations. Second, partially fine-tuned classifiers that retrain only the final few layers. And third, multi-stage classifiers that chain a cheap filter into an expensive one. Let us take them in turn. Start with probes. A linear probe is just a single direction in the model's activation space, fit with logistic regression, that scores how harmful the input looks. It is about as lightweight as a safety check can get. The paper tries 3 flavors. The mean token probe averages the activations across every token in the prompt, then scores that single pooled vector. It keeps a little signal from every position, but it has a weakness. On a long input, a tiny snippet of dangerous content gets drowned out by the average of everything else. The a probe fixes that. Instead of one average, it scores every token, smooths those per token scores with an exponential moving average, and takes the maximum along the sequence. So even one suspicious stretch lights it up. This is the cheapest method in the whole paper, and it punches well above its weight. The suffix probe takes a different angle. It appends a short question, asking whether the input contains harmful biological information. That nudges the model to gather the relevant evidence at one consistent token position, and the probe reads off the answer there. It costs a bit more, but it is slightly stronger. Family 2 is partial fine-tuning. Instead of training a whole new classifier, you branch off the main model at some layer and retrain only the layers from there to the end. The shared backbone is reused, and you keep a clean separation between the production model and the safety head. Why only the last few layers? Because their early probing already told them something. A linear probe stayed high quality almost all the way to the final layer, which means the safety-relevant information is present late in the network. So you do not need to retrain much of it to get a strong classifier. Family 3, multi-stage classifiers. Run a cheap classifier first. Anything it judges clearly safe, below a threshold, is waved through. Only the uncertain or suspicious cases get escalated to an expensive, high-capacity model. Most traffic never touches the costly stage. To know if any of this is worth it, you need baselines. We train dedicated classifiers from smaller models in the same family, labeled XS, S, M, and L, with overheads of about 0.6, 2, 9, and 25% of the largest models cost. The cheap methods have to beat those. And here is why the new methods are exciting on cost alone. Mean and probes need almost no extra computation, roughly 0.1%. The suffix probe is around 3%. And retraining, a single layer adds only 1 over the number of layers, landing near 4% total. Cost is not just compute, it is also latency. For prompt classification, only the suffix probe and the one retrained layer add delay, since they need an extra pass. And for checking the model's own output, probes can run concurrently with sampling, so they barely cost any wall clock time at all. Now the experiments. Training uses about 70,000 prompts, split evenly between attempts to extract bioweapon information and harmless examples. Everything is generated synthetically by the Claude 3.5 models from a written constitution, then twisted with Jailbreak templates, ciphers, and other languages. For testing, they deliberately measure generalization to jailbreaks the model never saw in training. Harmful test cases use held-out transformations plus real red team attacks from the Constitutional Classifiers project. Harmless cases come from wild chat and the hard subset of OR bench. And the metric matters here. They report log space a UROC, the area under the curve of true positive rate against false positive rate, but measured over log-spaced false positive rates from 1 in 1,000 to 1 in 10. In production, you live at very low false positive rates, so that low FPR region is exactly what you should grade. Here is the headline plot: detection quality against cost. The standout is the XL model with just one retrained layer. At roughly 4% overhead, it sits right up near the expensive options, basically matching a dedicated classifier built from a quarter-sized model. Spelled out, retraining a single final layer gives a classifier second only to retraining the entire model. It performs like the next size down, the L base model, the one with 25% overhead, while costing about 4%. One layer buys you almost all of the benefit. The ROC curves tell the same story for the probes. The suffix probe and the EM probe land close together, somewhere between the S and M baselines in strength. The plain mean of context probe, though, is the weak link. It comes in below even the smallest model. Put cost back into the picture, and the EM probe looks remarkable. For about 0.1% of overhead, essentially free, it beats a dedicated classifier with 2% of the model's parameters. The suffix probe edges a little higher, roughly matching a 4% overhead classifier. A natural next question: if one layer is good, are more layers better? They retrain the last 2, 4, 8, and 16 layers, and find, surprisingly, no clear trend. Past a single layer, the curve just wiggles inside the noise, staying a touch below the fully trained model. There is a genuinely strange wrinkle here. The partially trained models have much higher validation loss on the training distribution, yet they generalize better on the held-out test set. Being built on a bigger backbone seems to give out-of-distribution robustness that the training loss simply does not see. Now combine the cheap and expensive monitors. Using a probe or a one-layer model as the first stage, with the strong post-trained XL model as the second, beats the smaller baselines across the whole cost range, and the gap widens as you push the budget lower and lower. The best pairing, the EM probe or the single retrained layer in front, cuts the cost of the whole monitoring system by more than 10 times, with no significant drop in performance. You get frontier-grade detection at a small fraction of the original price. There is even a counterintuitive bonus. Sometimes the two-stage system slightly beats the strong classifier used alone. The reason? The two stages make uncorrelated errors, so a low first-stage threshold screens off many would-be false positives while keeping the true ones. The errors cancel. But here is the caveat that you must not skip. None of these classifiers have been stress-tested against adaptive adversaries who target the classifier itself. The red teamers in this study attack the policy model, blind to the monitor. Since safety is inherently adversarial, that gap is the whole ballgame. Multi-stage designs carry a specific new risk. If an attacker can convince the weak first stage that a prompt is harmless, the dangerous input never reaches the strong second stage at all. A cheap filter saves money, but it can also become the soft target. The takeaway is a strong cost-effectiveness result. Training a single layer rivals a quarter-sized dedicated classifier, and a per-token linear probe matches a 2% model for almost nothing. Reusing the model's own representations could make serious safety monitoring cheap enough to always leave on. The remaining work is to red team it.